All right, in this video, we will be going over section 1.4. This is about continuity and its consequences. Basically, we are going to learn what are the continuous functions and how we define continuous functions. Okay. All right, here we have our first definition. This is the definition of a continuity of a function at a given point. A function f is continuous at x is equal to c if limit as x approaches to f of x is equal to f of c. Okay, so in other words, the limit value should be equal to the function value at x is equal to c. Okay, here is the geometry. Suppose you have a function, graph of a function f of x like this. This is the graph of y is equal to f of x. Let's say this is your point C, and this is the value f of c. Or in other words, the function value at x is equal to c is f of c. Now, as you can see, what is the limit as x approaches to c, f of x? What is the limit? As x approaches to c from the right-hand side, your y value is approaching to this particular y value, but that y value is the function value itself. Even when the x approaches to c from the left-hand side, again, your y values are approaching to the same value, f of c, which is the function value. Okay, so this limit is equal to the function value at the point c. In that case, we say that our function f is continuous at this point c. Okay, so continuous means the limit value at x is equal to c is the same as the function value at that point. Okay. All right. The next definition. In the next definition, we discuss the left continuity and the right continuity. Here is what the definition says. A function f is left continuous at x is equal to c if the left limit is the same as the function value. Okay, this means the left limit as x approaches to c from the left-hand side, f of x is equal to f of c. That means the left limit is same as the function value. Okay, if that is the case, we say that function is left continuous and the function is right continuous at x is equal to c if the right limit is the same as the function value. Okay, let's look at an example here again. Suppose you have a graph of this form, f of x. Here is your graph. Let's say this point is 3, this point is 2, and this point is 4. Okay. Now let's observe a few things here. What can you say about left or right continuity of the graph of the function f of x? By the way, this is y is equal to f of x. Okay. What can you say about the left or right continuity or continuity of this function? Well, to determine that, we need to compute the left limit and the right limit at x is equal to 3. Okay. As x approaches to 3 from the left-hand side, f of x, what is my left limit? As you can see, as x approaches to 3 from the left-hand side, your y value is approaching to this particular y value, which is 2. What is my right limit? Limit as x approaches to 3 from the right-hand side, f of x is equal to, as you can see from the graph, as x approaches to 3 from the right-hand side, your y value is approaching to this particular value, which is 4. Okay. Now, what is the function value at x is equal to 3? F of 3. What is your f of 3 in this case? Clearly, your f of 3 is this value. This is the value, okay? Because you have this shaded circle here. So at x is equal to 3, your function value is 2. Now you should be able to determine what kind of a continuity you have here. Whether you have a left continuity, right continuity, or continuity. Okay, what can you say about that? Clearly, it is not continuous. because these two limits are not equal. Left limit and right limit, they are not equal. So it's not continuous. But here, as you can see, your left limit of the function at x is equal to 3 is same as the function value at x is equal to 3. Okay, so your left limit is same as the function value at x is equal to 3. What does that tell you? By this definition, this is satisfied, right? Your left limit is same as the function value at the point 3. So your C is 3 in this case. Okay, so function is left continuous. F is left continuous. At what point? For continuous, to say continuous, I will use CTS. Okay, here on nodes, I will be using CTS for continuous. Left continuous at x is equal to 3. Okay. By the way, it's not right continuous because your right limit is 4, the function value is 2. They are not equal. So it's not right continuous. Okay. All right. So let's move on to the next definition. This definition is about when do we say a given function is continuous on a given interval. Okay. So here is the definition. A function f is continuous on an interval I if it is continuous at every point in the interior of I, right continuous at every closed left endpoint, and left continuous at any closed right endpoint. Okay, let's look at few examples to understand this. Here is an example. I will make this a little bit bigger. Here is an example where your function is continuous on this open interval 1, 3. As you can see, you don't have any closed endpoints in this interval. It's an open interval. Here is the shape of a continuous function in that interval. Continuous means geometrically, what do you mean by continuous? Continuous means you should be able to draw the graph of that function in that interval without taking your pen off the board. Okay, if you can draw this continuously without taking your pen off the board, then your function is continuous. That's the idea, geometric. Okay, all right, here is an example of function which is continuous in this open interval. And then here is an example where your function is continuous in this interval. As you can see, here you have a closed left endpoint because this 1 is included in the interval, right? But 3 is not included. So you have a closed left endpoint. So in that case, if you want your function to be continuous, since this is a closed left endpoint, remember my definition requires my function to be right continuous at closed left endpoint. As you can see from this graph, your function is right continuous at x is equal to 1. Would you agree with me? Why is it right continuous? Because my function value at x is equal to 1. In other words, f of 1 is 1. It's clear. F of 1 is 1. And what is the right limit? Limit as x approaches to 1 from the right-hand side, f of x is also 1. So that means it is right continuous at this closed left endpoint. Okay. So by definition, this is an example of continuous function on the interval 1, 3, 1 included, 3 excluded. Okay. Here is an example of a function, graph of a function, which is continuous on the interval 1, 3. This time you have a closed right endpoint. Remember, at closed right endpoints, your function should be left continuous. As you can see, at this point, your function is left continuous because the function value is the same as the left limit of the function. Okay, so your function is, this graph of the function is continuous on this given interval. You have a shaded circle here. And here is an example where your function is continuous on the closed interval 1, 3. In that case, you have shaded circle at both ends. Okay, because both endpoints are included. So at the closed right end point, your function should be left continuous. It is left continuous, as you can see from the geometry. Your left limit is the same as the function value. And at the closed left endpoint, your function has to be right continuous. It is. In this case, your right limit is same as the function value. All right, let's move on. Next, we have this definition 1.15. We are going to talk about removable, jump, and infinite discontinuities. Okay. What do you mean by a removable discontinuity? First of all, suppose f is discontinuous at x is equal to c. We say that x is equal to c is a removable discontinuity if limit as x approaches to c f of x exists, but it is not equal to your function value at x is equal to c. Okay, let's look at an example for this. Okay, here I'm copying my definition again here. Again, removable discontinuity. We have a removable discontinuity at x is equal to c if the limit as x approaches to c f of x exists, but it is not equal to the function value at x is equal to c or f of c. Okay, so here is an example where you have a removable discontinuity. Think of a function like this. Okay, think of a function like this. All right, think of a function, graph of a function like this. This is the graph of the function f of x. Of course, it is here there is kind of a hole and the function value is here at x is equal to 2. And if you look at this graph, what is the limit as x approaches to 2 f of x? It is clearly 3, right? As x approaches to 2 from either sides. Your y value is approaching to a particular number. That number is nothing but 3. So the limit as x approaches to 2 f of x is 3. But what is the function value? What is f of 2? F of 2 is 5. As you can see here, f of 2 is, your function value is here. Now, notice that the limit value, the limit exists, limit as x goes to c, f of x exists, but that limit value is different from the function value at x is equal to 2. So we have a removable discontinuity at x is equal to 2. Removable discontinuity means you remove this point and place it somewhere else. Okay, that's the simple meaning of removable discontinuity. You remove that point and place it up there or somewhere here, somewhere down here. That kind of a discontinuity is called a removable discontinuity. The second type of discontinuity I want to talk about is jump discontinuity. When do you say that you have a jump discontinuity? Here is an example. Suppose you have a graph of a function f of x like this. This is the graph of the function f of x. Say this is 2, this is 3, and this is 7. Now, let's calculate the left limit and the right limit. Limit as x goes to 2 from the left hand side, f of x is equal to 3, right? As x approaches to 2 from the left hand side, your y value is approaching to this particular y value, which is 3. What is the right limit? Limit as x approaches to 2 from the right hand side, f of x is equal to 7. As you can see, both the left limit and the right limit exist in this case. Okay, the left limit is 3. Left limit at x is equal to 2 is 3, and the right limit is 7. But they are not equal. Your left limit is different from right limit. Then by this definition, we have a jump discontinuity. If you look at the definition again, if the left limit and the right limit both exist at x is equal to c, but they are not equal, then we have a jump discontinuity. Okay, as you can see here, both left and right limit exist, they are not equal. In that case, we are going to have a jump discontinuity. Jump discontinuity means geometrically, if you walk along this graph like this, when you come to here, you have to jump over here and continue your journey from there. Okay, you have to kind of jump from here to here when you come here. Okay, so that's why it's called jump discontinuity. And then the next type of discontinuity is infinite discontinuity. Here is an example. Suppose you have a vertical asymptote here. The graph of f of x looks like this. Okay. We say that we have an infinite discontinuity if one or both of these limits is infinite. Okay. If the left limit, as limit x approaches to c from the left hand side, f of x is infinite, or limit as x approaches to c from the right hand side, f of x is infinite, or both. Okay, in this case, limit as x approaches to c from the left hand side, let's say this point is 5. Limit as x approaches to 5 from the left hand side, f of x is equal to plus infinity. So we can immediately conclude that by this definition, we have an infinite discontinuity at x is equal to 5. If one of these limit is infinite, you have an infinite discontinuity at that point. Again, let's recall this. Removable discontinuity means your limit exists, but the limit value is not equal to the function value. Here is an example. The limit exists, the limit value, limit as x approaches to 2, f of x is equal to 3, but the function value at x is equal to 2 is 5, which is different from the limit value. In that case, we have removable discontinuity. When do you have a jump discontinuity? If both left limit and the right limit exist and they are not equal. Here is the example. Both left limit at x is equal to 2 and the right limit at x is equal to 2, they both exist, but they are not equal. In that case, you are going to have a jump discontinuity like this. And here is an example of an infinite discontinuity. Okay. One or both of these should occur. In this case, as you can see, limit as x approaches to 5 from the left-hand side, f of x is infinite. So we are going to have an infinite discontinuity at x is equal to 5. All right, let's move on. Let's work on this example now. Discuss the type of discontinuity at x is equal to -3, 2, and 4. Okay. Let's work on the point at x is equal to -3 first. Okay. What happens at x is equal to -3? Let's compute the left limit and the right limit. Limit as x goes to -3 from the left-hand side, f of x is equal to, clearly it is 2, right? The left limit as x approaches to 3 from the left-hand side, f of x, your y value is approaching to this particular y value, which is 2. And limit as x approaches to -3 from the right-hand side, f of x is equal to 5, right? X approaches to 3 from the right-hand side, your y value is approaching this one. This is 5. Okay. All right. Now, what kind of discontinuity are we going to have here? As you can see here, both left limit and the right limit exist at x is equal to -3, but they are different. Okay. Both left and right limit exist, but they are different. That means we are going to have a jump discontinuity. It is clear from the graph. See, if you walk along the graph, when you come to this point, you have to jump over here and then start your journey again. Okay, you have a jump there. So we have a jump discontinuity. Jump discontinuity. Done. What about at x is equal to at x is equal to 2? What kind of a discontinuity are we going to have? Well, as you can see here, the limit exists. Limit as x approaches to 2, f of x is clearly 1. When x approaches to 2 from both sides, your y value is approaching to the same value, this particular value, which is 1. But your function value at x is equal to 1 is 4, which is different from the limit value. The limit exists, but the limit value at x is equal to 2 is at x is equal to 1. Pardon me, this should be 2, okay, f of 2. The function value at x is equal to 2 is 4, but the limit value as x approaches to 2, f of x is equal to 1. They are different. So by the first definition, first part of this definition, we have a removable discontinuity. Removable discontinuity at x is equal to 2. Here also you could write at x is equal to -3 in the previous part. All right. What about at point x is equal to 4? Clearly, you have an infinite discontinuity, right? Because limit as x approaches to 4 from the left-hand side, f of x is equal to infinity. Okay, so there's an infinite discontinuity at x is equal to 4. Infinite. Continuity at x is equal to 4. All right, let's move on. All right, next we have this theorem 1.16, continuity of simple functions. Okay, constant, identity, and linear functions are continuous everywhere. Okay, what is a constant function? Any function of the form f of x is equal to k, where k is a constant, is called a constant function. And here is the identity function, f of x is equal to x. Your input is same as your output. Okay, here is an example of a linear function. Linear function is a function of the form f of x is equal to mx plus c, where m and c are some real numbers. Okay, so these types of functions are continuous everywhere. That's what this theorem, part A of the theorem, tells you. What do you mean by continuity? Continuous in terms of limits. Well, in terms of limits, for every k, c, m, and b in R, we have limit as x approaches to c, k is equal to k itself, because if k is a constant, as x approaches to c, nothing happens, right? The constant stays as constant itself. And then limit as x approaches to c, x, your function is x in this case, that is equal to c. What you do is you just plug in the value c in your function. If you plug in value c here, you get c. Again, the limit of this function, mx plus b, that is the linear function. How do you find the limit? Because you know that your function is continuous. This linear function is continuous from this part. This limit has to be true. This limit should be equal to mc plus b. Simply what you do is you plug in this value c in the function for x. Okay, then you get, if you plug in x is equal to c here, you get mc plus b. That is the limit. Okay. All right. Or in other words, if you want to show that this linear function is continuous everywhere, you need to show that limit as x approaches to c, mx plus b is equal to mc plus b for any c value. If I can show this limit statement, that means by definition of continuity, this linear function is continuous everywhere, right? All right, the next part of that is power functions are continuous on their domains. Okay, in terms of limits, if a is a real number, k is a rational number, then for all x values, x is equal to c, at which x to the power k is defined, we have limit as x approaches to c, ax to the power k is equal to a times c to the power k. What this means is that if this point c is in the domain of this function, this power function, then to find the limit, you can plug in this value for x. That's all it tells you. Okay, that's just the definition of continuity. If you know that this function is continuous, then you can plug in this value. If you know that this function is continuous at x is equal to c, then you can plug in the value c in the function to find the limit. Okay. All right. We are not going to prove all these, but I will give you a proof which shows that linear functions are continuous everywhere. Okay. So let's establish this limit statement. Let's see if we can prove this one. I'm going to use the algebraic definition of limit that we discussed in section 1.3 to prove this one, prove this limit statement. All right. So we are going to prove this one. First of all, what does this limit statement mean? What is the definition of this limit statement? If you want to prove this one, what do you have to prove? We need to show that for all epsilon greater than 0, there exists delta greater than 0 such that if absolute value of x minus c is bigger than 0 and less than delta, then the absolute value of f of x minus L should be less than epsilon. By the way, this is my f of x, this is my L. As you can see here, this is my f of x, this is my L, right? L is the limit. Okay, how do we start with the proof? Well, start with any given epsilon greater than 0. Given epsilon greater than 0, choose delta to be epsilon divided by the absolute value of m. You will see why I am making this particular choice, okay? Why I am taking my delta to be epsilon over absolute value of m when we do the calculation, okay? Now, what do you need to prove? We need to prove that if this happens, this happens. That's all we need to prove. Then we are done, okay? So, if absolute value of x minus c is less than delta, remember my value of delta now is this one, epsilon over absolute value of m. Then we have, let's compute this difference. The absolute value of mx plus b minus mc plus b. That is equal to m times x minus c, the absolute value of that, of course. Now, this is equal to m times absolute value of m times, I can factor out this m as the absolute value of m times absolute value of x minus c. But I know that my absolute value of x minus c is less than delta. So this has to be less than absolute value of m times delta, right? Because my delta is bigger than this one. So I put a bigger thing here in the right hand side. Now I'm going to use the choice of delta. Remember, I took my delta to be epsilon over absolute value of m. That's where I decided that, remember, at the end of the day, what do I need? I need this to be less than epsilon, right? If I want that to be less than epsilon, I want this to be epsilon. If this is epsilon, I'm done, right? So to make this epsilon, I choose my delta to be epsilon over absolute value of m. This is by choice of epsilon, you have epsilon over absolute value of m. Now, as you can see, this absolute value of m and this absolute value of m, they are cancelled. You get epsilon. You get mx plus b minus mc plus b. Of course, the absolute value of that less than epsilon. That's what exactly I wanted to prove. If this happens, this happens. As you can see, the absolute value of that difference is less than epsilon. Okay, so this completes the proof. That means this limit statement is true by the algebraic we use the algebraic definition to prove this one. Okay. By the way, here we made a very important assumption, that is m is not equal to 0. Okay, If m is equal to 0, you cannot divide here, right? Because you cannot have 0 in the bottom. Why do I assume m is not equal to 0? Well, m is equal to 0, this part goes away, right? Then you have a constant. But the constant case is talked about here. Okay, that case is covered in this first part. So we are not interested in that case. We are interested in the case when m is not equal to 0. All right, let's move on. Now we can apply. Let's see some applications of this theorem. Okay, so first part is clear, right? A limit as x approaches to 2, 3 is equal to 3 itself by the first part of the theorem. Okay, we have a constant function, limit as x approaches to c, constant is equal to constant itself. Okay, and the second part, part B, how do you do part B? Limit as x approaches to 1 over x. How do you handle this one? Can you apply any of the parts in this theorem? This is the theorem I had. Can you apply one of these parts there? Well, we can apply this part. See, if we have a power function of this form, a times x to the power k, then you can find the limit as x goes to c, a times x to the power k, by plugging the c value for x. But you need to make sure that your function is defined at the point x is equal to c. Okay? If your power function is defined at the point x is equal to c, then you can plug in x is equal to c in this function to find the limit, and this is going to be your limit. Of course, this one is a function of that form. Notice that 1 over x is nothing but x to the power minus 1, right? It takes the form a times x to the power k, right? What is your k? K is minus 1. What is your a? A is 1. There's an invisible 1 here. So my function, this function takes this form, even though it's not, it doesn't look like that. Okay. So that means, by the way, another good thing here is that this 2 is in the domain of this function. Okay. 2 does not mess up my expression. So to find this limit, all what you need to do is you just plug in the number 2, 1 over 2. That's the limit. Okay. And then part C, very straightforward. Limit as x approaches to 6, you have a linear function, right? Mx plus b. Here you have a linear function. This is your m. Your b is minus 3. Remember, if you have a linear function, limit as x approaches to c, mx plus b is mc plus b. So if you straight away plug in the value 6 in the function, 2 times 6 minus 3, which would be 9. That's the limit. Okay. All right. Let's move on. Next, let's look at this example. Describe the continuity or discontinuity of the given piecewise function that follows at x is equal to 1 by using graphs to determine the left, right, and two-sided limits at x is equal to 1. Then describe the intervals on which the function is continuous. Okay, let's work on this one. First of all, this is a piecewise function, right? By your pre-calculus class, you know how to graph a piecewise function like this. If you graph this piecewise function, you will see that your graph would look like this. In the left-hand side of 1, when x is less than or equal to 1, you have this parabola that would have this shape. And when x is greater than 1, you have this straight line x minus 1. That's what you have here. Okay. All right. Now let's compute the left and right limits to discuss the type of discontinuity we have, or continuity, okay, at x is equal to 1. Well, I'm going to compute the limit, the left limit, x approaches to 1 from the left-hand side, f of x is equal to 3, right? Your left limit is 3, because as x approaches to 1 from the left-hand side, your y value is approaching here, right? This is 3. And what is the right limit? Limit x approaches to 1 from the right-hand side, f of x is equal to, right limit is 0. As x approaches 1 from the right hand side, your limit, your y value is approaching to this particular y value, which is 0. Okay. All right. Now, as you can see, left and right limit exist. Both left and right limit exist, but they are not equal. What kind of a discontinuity are you going to have? Clearly, it's a jump discontinuity, right? That's the definition of jump discontinuity. You have a jump discontinuity at x is equal to 1. Okay. All right. Can you say anything about right continuity and left continuity? What kind of continuity do we have here? For that, I need the function value, right? In addition, I need to compute the function value at x is equal to 1. What is f of 1? F of 1 is clearly 3 because I have my shaded circle here. So f of 1 is 3. Now, as you can see, your function value at x is equal to 1 is the same as your left limit at x is equal to 1. Limit as x approaches to 1 from the left-hand side, f of x is equal to 3. Your function value at x is equal to 1 is also 3. So what can you say about the left continuity? Your function is left continuous because the left limit is the same as the function value at x is equal to 1. So the function is left continuous at x is equal to 1. Continuous at x is equal to 1. Okay. You could say f is left continuous at x is equal to 1. All right, next, the intervals on which this function is continuous. On what intervals would this function be continuous? Notice that to the left of 1, when x is less than or equal to 1, this is the piece of the function. Clearly, this is a continuous function. You can see that from the graph as well. It's a continuous function. So your function is continuous on the interval from -infinity to 1. 1 included here, because this part, if you look at this piece, here you have the shaded circle here. So your function is continuous. F is continuous on these intervals, -infinity to 1. This is closed. 1 is included because this is a shaded circle. Okay. Your function is left continuous at this closed right endpoint. Okay, so your function is continuous on the interval -infinity, 1, 1 included, and then your function is continuous again in this interval when x is bigger than 1. Okay, and the other interval is 1, infinity. This time 1 is excluded. I cannot include 1 because we have an open circle here. Okay? So beyond 1, your function is continuous. Continuous means you should be able to draw the graph without taking your pen off the board. This piece also you can draw without taking your pen off the board. Okay. All right. Let's move on to the next slide. Next, we have the extreme value theorem. The extreme value theorem. Okay, here is the formal statement for the extreme value theorem. If f is a continuous on a closed interval a comma b, then there exist values uppercase m and lowercase m in the interval a comma b, closed interval a comma b, such that if uppercase m is the maximum value of f of x on a comma b, and f of lowercase m is the minimum value of f of x on the interval a comma b. Okay, let's look at an example to understand this. Okay, suppose your function looks like this. This is the graph of f of x. Okay, say this value is 2, this value is 1. This is not drawn to a scale. Okay, this value is say 5. This value is 3. Okay, now as you can see, this is the graph of y is equal to f of x. Here is the graph. Okay, as you can see, this graph is continuous on the closed interval. f is continuous on 1, comma 2, right? See, I have a shaded circle here. My function is left continuous at this right closed endpoint, and my function is right continuous at this left closed endpoint. Okay, it's clear from the graph. So this is a continuous function on the closed interval 1, comma 2. Can you find such uppercase m, such an uppercase m, and such a lowercase m in this case? Okay. Well, what is your uppercase m? So the theorem statement tells you that there exist values uppercase m and lowercase m such that f of uppercase m is the maximum value of f of x on a comma b. Well, my uppercase m in this case clearly would be this point, right? Because at this point, your y value would be this height. This is the y value. And that is the biggest y value that you can have on the graph of your function, right? This is the biggest y value. So clearly, such an uppercase m exists in this case. Okay, this is the candidate for your uppercase m. That is the maximum value. F of m is the maximum of f of x on the interval 1, comma 2. That is the max. F of m is the maximum y value. This is f of m, by the way. This is f of m. That is the maximum of f of x on the interval 1, comma 2. And then what about the lowercase m? Do we have a lowercase m in this case? Is it clear from this figure? Lowercase m is the point such that f of lowercase m is the minimum of f of x on the interval a comma b. In this case, my a comma b interval is 1, comma 2. What is the candidate for lowercase m in this case? Clearly, the candidate for lowercase m is 2, right? This is your lowercase m. Why? Because if you walk along the graph, this is the minimum y value that you can have, right? This is your f of lowercase m, which is the minimum of your function f of x on the interval 1, comma 2. Okay, so this is actually f of lowercase m. Write it better. This is f of lowercase m. Your m is lowercase m is 2 in this case. Okay. So f of m is the minimum of f of x on the interval 1, comma 2. Okay. Such uppercase m and lowercase m clearly exist by looking at this graph. Okay. By the way, do we really need this interval to be a closed interval in the statement of the theorem? Can we have an open interval? The answer is no. You have to have a closed interval in order for this theorem to be true. Okay, you cannot replace this closed interval by an open interval. Why is that? Let me show you why. Okay, think about a function like this. You will see that. Not that. How about this? Say this is 2, this is 7, say this is 3, this is 5. Okay, this is the graph of y is equal to f of x. Okay, as you can see, this time my graph is not continuous on the closed interval 2, comma 7. Do you see that? In this closed interval, it's not continuous because see here at x is equal to 7, your function is not even defined. How can that be continuous then, right? It is continuous only on this interval. Okay, 2, comma 7, 2 is included, 7 is excluded. Okay. As you can see now, you cannot find the candidate for uppercase M. Can you find a candidate for the uppercase M? That means you need to find an X value such that f of M is the maximum value. Can you find such an M here? No, because the only potential candidate is 7. See, your function, your Y value would be highest here, but that candidate is not in your domain. Your function is not defined at 7. Okay, so that means there is no such M. Okay, there is no M on the interval 2, 7 such that f of uppercase M is the maximum. Is the maximum of f of x on the interval 2, 7. This 7 is not included. Okay, open interval. Okay, so you cannot find such an M. You cannot find M here. If you find M here, your Y value is here. You can go a little bit further and find a bigger Y value. So the only potential candidate is 7 for your uppercase M, but 7 is not in your domain. Your function is not defined at that point. Okay, so your function is not continuous in the closed interval. In that case, you cannot find an uppercase M such that f of M is the maximum of f of x on the interval 2, so in this theorem statement, this interval being closed is a must. It has to be a closed interval. If it is an open interval or half open, half closed interval, you cannot apply the theorem. All right. Next, we have this particular theorem, intermediate value theorem. This is also an extremely important theorem in calculus. Here is the statement of the theorem. If f is continuous, function on a closed interval, again our interval is closed, okay, then for any k strictly between f of a and f of b, there exists at least one c in the open interval a comma b such that f of c is equal to k. Okay, what does this mean? If you read the statement again, f is continuous function on the closed interval a comma b, then for any k strictly between f of a and f of b, there exists at least one c in the open interval a comma b such that f of c is equal to k. Okay, let's look at the geometry again to get an idea about what's going on here. Okay, say your a is here and your b is here. Okay, and let's say the f of a is here and your f of b is somewhere here. This is your f of b. And this number k is strictly between f of a and f of b. That means your number k has to be somewhere here, right? Strictly between this number and this number means it has to be somewhere on this interval. Let's say your k, number k is somewhere here. And then let me draw a dotted horizontal line like this. I'll tell you why I'm drawing that. Now, let's make few observations here. Okay, I know that my function is continuous on this closed interval. Okay, my function is closed in this closed function is continuous on this closed interval means if I take these 2 points, this point and this point, I should be able to join my graph should be a continuous function, continuous graph joining these 2 points, right? If it is continuous, these 2 points should be joined with a smooth curve like this, right? That's the graph of my function. That's what we mean by continuous, right? So can you draw a graph? Can you join these 2 points? Can you join these 2 points with a continuous curve without crossing this blue line, blue dotted line on this interval a comma b? That means somewhere on this line. Okay, can you draw the graph of your function f of x without crossing this red piece of line? You cannot, right? If you join these 2 points, because you know that your function is continuous, so there has to be a continuous way of joining these 2 points, right? No matter how you join these 2 points, your function is going to cross this blue line at some point on the interval a comma b. See here, if you take a graph like this, your graph is going to cross the blue line at this point. Let's say this point is C. And if your graph is like this, your graph is going to cross the blue line at this point C. And this C is the candidate for this C, that is that C, okay? Someone could be wondering, why can't we draw this graph like this? That way, my function does not cross this line segment, right? But if you draw your graph like this, it is not a graph of a function by vertical line test. See, if you draw a vertical line somewhere here, your vertical line is going to intersect the graph at 2 points. That means it's not a function anymore, okay? We are talking about functions here. So the only option that you can join these 2 points with a smooth continuous curve is to cross this blue line somewhere on this interval, okay? So now let's say your graph looks like this. Then as you can see at this point, I'll take this point to be C, okay? At x is equal to C, what is my y value? At x is equal to C, my function value is k, okay? So f of C is equal to k. So that means such a C exists, okay? There exists C in this interval, in this open interval a comma b, such that f of C is exactly that value k, which is stuck between f of a and f of b. That is the geometric idea of the intermediate value theorem, okay? All right, let's move on. Let's look at this example. This is an application, a straightforward application of intermediate value theorem. The function f of x is equal to x cubed minus 3x plus 1 is continuous everywhere. It is given to us, okay? It is given that this function is continuous everywhere. Use the intermediate value theorem to conclude that there is some point C for which f of C is equal to 2. Okay? How can I apply the intermediate value theorem here? Well, to apply the intermediate value theorem, I'm going to view this number as my k. See, in the intermediate value theorem statement, this looks like, if you compare this one with this one, this looks like my k value, okay? So what I'm going to do is, I'm going to find two x values such that my k value is strictly between the two y values corresponding to the two x values I picked, okay? Here is what I mean. It's a lot. I'm saying a lot, okay? So here is what I mean. Let's compute f of 0. I'll tell you why I'm computing f of 0, okay? In this case, I'm going to take this 0 as my a, okay? The value of a is 0. So if you compute f of 0, if you plug in 0 here, you get 1, right? And next, I'm going to compute f of, say, 2. You compute f of 2, which is going to be 3. You plug in 2 here, which is 8. 2 here, 6. 8 minus 6 is 2, plus 1, 3. Okay. So I'm going to view this number as my b. The value of b is 2. Okay. All right. Now notice that this is my f of a, because this number is a, right? I'm taking this number to be a and this number to be b. Then this is my f of a. This is my f of b, right? And notice that the value of k is strictly between these two numbers, 1 and 3. If that is the case, from the intermediate value theorem, we can conclude that by intermediate value theorem, there exists C in the open interval a comma b. Notice that my a is 0 in this case, b is 2. 0, 2, such that f of c is equal to 2. Okay, that's a straightforward application of intermediate value theorem. See, as you can see, I immediately tried these two values, right? How did I know that I should try 0 and 2? Why didn't I try some other numbers? Well, I did my homework before. Okay, you have to keep trying numbers so that you see this number is stuck between these two numbers. Okay, there's no obvious straightforward way of finding this combination 1 and 3 or some other two numbers. So the bottom line is you need to make sure that at the end of the day, this k value is between these two y values you compute. Okay, if certain two y values are not going to work, try some other x values. Okay, try some different x values. Then at some point you will get two numbers such that your k value is stuck between those two numbers. Okay, I did my homework to figure out these two values. All right, that's a straightforward application of intermediate value theorem. Let's look at another. Before we go to the next example, let's go over this theorem. A function can change the sign only at roots and discontinuities. Okay, so here is the formal statement. A function f can change sign from positive to negative or vice versa at a point x is equal to c only if f of x is 0, undefined, or discontinuous at x is equal to c. Okay, this tells you conditions under which you can have a sign change of your function. Okay, the first situation that you can have a sign change is that you have a 0 of your function. 0 of your function means at that point, at that x value, your y value is 0. As you can see from the graph of f of x here, here is the first example we are going to look at. At this point, at x is equal to 1, your f of x is 0, right? So that means this 1 is the 0 of your function. 1 is the 0 of f of x. 0 of f of x. See, at a 0, your function could change the sign. As you can see, to the left of this number 1, your function values are positive. To the right of that number 1, your function values are negative. If you take an x value somewhere here, your y value is negative. As you can see, your function changes the sign at this point, at this 0. Okay, so that means a function could change the sign at a 0. And then another situation where your function could change the sign is at a point where your function is undefined. Here is an example for that. At x is equal to 5, clearly your function f of x is undefined because you have a vertical asymptote there, right? Your function is undefined there. When your function is undefined, as you can see from the geometry of this picture, again your function changes sign at this point 5. To the left of 5, you have positive y values. When you go to the right of 5, you have negative y values. Okay, your sign changes from positive to negative when you go from left to right at 5. Okay, and here is the other situation where you can have a sign change. This is a situation where you have a discontinuity. As you can see, you have a jump discontinuity here, right? Here to the left of 2, your function is positive, and to the right of 2, your function is negative. Okay, these are the 3 cases where you can have a sign change for your function. Okay, all right, with this in mind, let's do our last example. Determine the intervals on which the function that follows is positive or negative. You may assume that the function is continuous everywhere. So this is the function given to us. We are given that this function is continuous everywhere. If this function is continuous everywhere, notice that from the previous theorem, we are not in these two situations, right? If it is continuous everywhere, it is not discontinuous at any point. It is not undefined. Okay, so we are only in this case. So that means the graph of this function or this function can change the sign only at zeros of this function. because we are out of these two cases. Okay, so my function can change the sign only at zeros of my function. Okay, because this is continuous function. It's given to us. Okay, so don't forget our goal. Okay, we need to determine the intervals on which the function that follows is positive or negative. How do we determine the intervals where the function positive or negative? Well, what I'm going to do is I'm going to find the zeros of this function. To find the zeros of this function, I'm going to set my function to 0 and I'm going to factorize this expression. Then you get this expression. Now setting each individual factor to 0, you get these three zeros. The first 0 is 0, the second 0 is 1, the last 0 is -2. Now what I'm going to do is I'm going to make a sign chart. Okay, this is my -2. I place my -2, which is the smallest number here. And then I have a 0. Finally, I have 1. Okay, now remember by previous theorem, my function can change the sign only at these 3 points. Okay, it cannot change the sign at any other points. These are the only points that my function could change the sign. Okay, if that is the case, if my, let's focus on this interval. If my y value for a certain x value in this interval, for example, say I pick an x value here and I find my y value to be negative, then all the y values for all these x values have to be negative in that interval. Why? Because your function can change the sign only at these points. Okay, your function cannot be like this. Your function cannot come and cross the x-axis somewhere here, because if it crosses, this is going to be a 0. No, that's not possible. These are the only zeros, and at these points only your function can change the sign. So to determine where my function is positive and where my function is negative, what I'm going to do is I'm going to pick a point from each interval. I'm going to pick a point from this interval, -infinity to -2, and I'm going to pick a point in this interval, and I'm going to pick a point in this interval, and finally I will be picking a point in this interval. Okay, so let's pick a point in this interval, -infinity to -2. I'll choose -3, and then I pick a point in this interval. I'll choose -1, and a point from this interval. I'll choose 0.5, and a point from this interval. I'll choose 2. Then what I do is I compute the corresponding y value or the function value. Corresponding function value at those chosen points. Okay, let me compute those values. All right, y value at x is equal to -3 is -36. You can check this out. You can compute it and see. Y value at -1 is +6. And this is -1, and the y value at 2 is 24. Notice that I picked the point -3 from this interval, -infinity to -2. And for this chosen x value, my y value is negative. That means all my y values has to be negative in this interval. Okay, because my function can change the sign only at these 3 points. Okay, so if my y value is negative for a 1x value, then my y value has to be negative for all the x values in this interval. Okay, so that's the idea. So in this entire interval, my y value has to be negative. So let me put a bunch of negative signs in that interval. Okay, and at x is equal to -1. -1 is the number that I picked from this interval. My y value is 6, which is positive. So that means for all the x values in this interval, your y value has to be positive. Okay. And here, similarly, all the y values in the interval 0, 1, corresponding to the interval 0, 1 has to be negative. Because at x is equal to 0.5, your y value is negative. So for all the x values in this interval, your y value has to be negative. Why should it be negative? Because your function cannot change the sign except at these points. Okay, so if your y value is negative for a one x value in this interval, on that entire interval, your y value has to be negative. Similarly, here you have positive. So we can write the intervals where your function is positive and intervals where your function is negative. Okay, f is positive on -2, 0 union 1, infinity, these two intervals, this interval and this interval, and negative on -infinity, -2 union 1, infinity. Pardon me, negative on -infinity, -2, 0, okay, this is the set where your function is positive, and this is the set of x values where your function is negative. Okay. All right. With that, we conclude section 1.4. I'll stop there, and I'll see you next time.